Today we're going to test the theory that a trash can can protect your radio equipment from an EMP. I'll be honest, this is a subject that I was pretty hesitant to jump into for a number of reasons. One, all the information out there on EMPs, so much of it is just garbage on the internet. So you really have to do a lot of digging to get down to the truth, which is what I've been trying to do for over 2 years, figure out what the real truth is about how EMPs work. But where this all got started was about 7 years ago. I went and had a surgery done in another state. And when we flew there, the doctor's a pretty well-known doctor in his field. But we were just sitting there having a discussion about where we lived. He's like, "Oh, you guys live over in that part of Oregon." I'm like, "Oh, I don't know what you meant by that, but okay." And he asked, like, what do we do on our property? And I said, "Well, when we get back, we have over 100 fruit trees that are going to show up that we have to plant." And it really piqued his interest, and he started talking, and I wasn't sure where he was headed. I couldn't figure out why is he so interested in our fruit trees, because I was planting them to make apple cider. At the time, I was hoping to get involved commercially making apple cider. And further in the discussion, I find out this guy's a prepper. He's big time into it. I mean, like head over heels into prepping. And the only thing I knew about preppers at the time were the TV shows that you saw. And I can't remember the name of them, the guys that went nuts building bunkers, and, it was a ridiculous TV show. But that put preppers in I think a really bad light, looking back on it now. At the time, I was not a prepper. And so, it really caught me off guard what this guy was saying. He steered me to a couple books that I read, and it kind of resonated with me that, our infrastructure, our actually society in general, is kind of a deck of cards, and it wouldn't take a whole lot to collapse that deck of cards. And one of the things, he got me hooked after, I should say, he steered me to those books. I didn't actually read them. In my line of work, I do quite a bit of driving, so audiobooks is usually the way I absorb information from books. Once in a while, I'll actually read a book, but geology books I read, but fiction books, it's just usually not my thing until I stumbled across these end of the world type books, apocalypse books. It just kind of piqued my interest. Not that I'm saying that I think any of that stuff's imminent or going to happen right away or happen at all. But the genre kind of just clicked with me, and so I've been listening to quite a few of them, and all of them that are EMP based, it's the end of the world as we know it. Some country has popped an EMP over the United States and everything collapses. Even your wristwatches quit working and blah, blah, blah. And so it got me thinking about radio equipment and what EMPs really do. And I did a whole lot of actual reading. It's one of the times it's nonfiction, so I'll sit and read that kind of stuff all day long. Started digging into what documentation you can find, factual documentation you can find about EMPs. And let me tell you, it's sometimes a little hard to find because the government, they probably don't want everybody knowing exactly how their weapons work, because they've got obviously weapons that are designed, nukes that are designed to create EMPs. So, and there's other smaller devices. When I say smaller, it means it's a smaller radius that it'll have an EMP effect. So, I did a whole lot of reading over the last couple of years trying to figure out what's true, what's not true, because every one of these books, almost every one, like anything that's electronic dies. End of the world, for most people, it's all dead. And the more I dug into this, the more I found that's probably not quite true, because there's different EMPs that you can have, different EMP ratings, I guess. And there's like CMEs that were caused by the sun. You got the big like event that happened in the 1800s. I can't remember what year it was, but it burnt telegraph lines up like crazy. And you know, if that was to happen today, our power lines are very vulnerable to something like that, at least from what I can determine and what the government has come out and said. We're pretty vulnerable to that kind of event. So let's kind of dive into this a little more and discuss it. But before we dive into the in-depth discussion about the different types of EMPs and so on and so forth, a discussion, anytime I see a discussion on the internet from usually hams, is why, you know, somebody will ask about EMP protection or whatever. And inevitably, somebody will pop up. Why would you even worry about it if we have an EMP? That's the least of your concerns is your radio equipment. Well, that's really not true. If you look at any emergency disaster of any kind, communications play a vital role in any emergency situation. Look from police agencies, wildland firefighting, take any big disaster, whether it be a hurricane, floods, earthquakes, you know, you name it. One of the first things that everybody tries to reestablish is communications. So there is a viable need to protect your gear from an EMP. Like mine sitting out here on the desk all the time, probably not going to be too well protected. If you're serious about it, should you have a backup radio maybe and something that will protect it? Well, if you think that this is an actual possibility, then I say, yeah, you should. So let's go ahead and dive into the different types of EMPs that we're talking about. Let's go through a few of the terms that you may run into. This first one is an NEMP, a nuclear electromagnetic pulse. This is the one everybody's always scared of, that North Korea or whatever country is going to set off over the United States. The next one you'll see is an HEMP, a high altitude electromagnetic pulse. Again, caused by a nuclear weapon going off at a high altitude, usually 100 to 300 and some miles above the surface of the earth. The other one that you'll see on occasion is a CME, which is a coronal mass ejection from the sun. And this causes a form of an EMP, which we'll cover here in just a minute. I'm not going to spend a lot of time on this just because I want to get into the testing part of what we can do to protect our equipment. But quickly, nuclear EMP actually has three components to it, more or less three different pulses that come out of it. The first one is an E1 pulse, the second is E2, and then E3. The E1 pulse, actually all of these are generated by what's known as the Compton effect, and there's a ton of reading you can do on the Compton effect, but it's more or less gamma radiation from the nuclear explosion super energizes the upper atmosphere, and then we've got these EMP pulses from that. That's really a basic overview of it, but that's kind of what happens. So the E1 is the one that seems to create the most controversy among all these prepper groups and whatnot, is what's going to happen when that one happens. And the reason why is that E1 pulse is extremely fast. It's very short-lived, but it contains a tremendous amount of energy. But what really is the killer on this one is the rise time of it. The typical rise time you'll see is between 5 and 20 nanoseconds. And the whole pulse only lasts between 1,000 to maybe 1,500 nanoseconds from start to finish. In comparison, a lightning strike, which, by the way, usually contains a lot more energy on a localized level than an EMP pulse. You know, I'm talking about like right at your station, if you get hit with lightning, there's a much more energy locally from that lightning strike than an EMP. But that's just kind of a side note. The typical lightning strike, the rise time to the peak of the pulse is about 1 to 10 microseconds. Now, for those of you who don't know, when we're talking about the EMP pulse, it's 5 to maybe 20 nanoseconds, which it takes 1,000 nanoseconds to make 1 microsecond. So you can see the rise time, it's much, much faster on the EMP pulse, that E1 pulse, which makes it really hard to stop. Most lightning suppression devices, surge suppression devices and such were not made to react that fast. You know, lightning protection, not a problem. It can catch that lightning at that 1 micro to 10 microseconds. But 5 to 20 nanoseconds, you have to have a very fast acting device to stop that. And most of the protectors you see on the market today just are not capable of it. So if you've got lightning protection and you think you're protected from EMP, you're probably really not, at least not the E1 pulse. And the other thing, this is the one that seems to garner the attention that it's going to destroy every electronic device out there because it's just something we can't stop. And, you know, it's this magic wave that comes through the air. And it's really not. It's a radio wave of sorts. It's more or less, from what I've been able to dig through all the material, it's pretty much almost DC to daylight electromagnetic pulse that comes off of this. It's, you know, obviously not clear down to DC, but very low frequency, clear up to high microwave frequencies. But the majority of this pulse, like 90% of its energy, is carried between 10 and 100 megahertz. So that gives us something to work with down the road here when we're starting to do our testing. Again, the majority of this energy from the E1 pulse is between 10 and 100 megahertz. So keep that in mind for the testing we're about to do. Now the next pulse is, or the next component is the E2, which it's more like a lightning pulse, I guess you could say. It's happens about 1 microsecond to maybe 1 second after the initial explosion. It's got a slower rise time to it. And most things that are lightning protected will stop this E2 pulse. So it doesn't usually garner as much attention. If it's critical, it's usually already protected with lightning protection. Now that's assuming the lightning protection survives the E1 pulse, which there's a lot of debate on whether they will or won't. So from there we'll jump to the E3, which is the last component of this. And it generally resembles very much a CME type event. It's very long-lived. It can last from, you know, several seconds up to 200 seconds, maybe even more, maybe even up to a day long of different releases of energy from this E3 pulse from all the information I've been able to read. It's very, very similar to a event caused by the sun. This is the one, the wavelengths are very long on it, and power lines are really susceptible to this one because they act as very long antennas and induces voltage across them, and then we get huge problems. Now the E1 and E2 can also do that, but it's more likely to affect smaller components, whereas E3, you're looking at, it needs a long piece of conductor out there, and our power lines are the perfect example of that, and it will pick that wave up, induce voltage across power lines and destroy them, and transformers. So that's kind of a really brief down and dirty overview of the different EMPs and the frequencies and all that kind of stuff. And what it really boils down to, and trust me, there's other types of EMPs out there, and we're not going to dive into all that, but these are the ones that seem to be the big concern to everybody. So we're going to stick with this. And what all this garbage really means is, how can we protect ourselves, especially from that E1? The E2 and E3 are not as big a concern because common lightning protection can take care of those. It's that E1 that we need to worry about. And I'd like to emphasize, if you're worried about EMPs and you've read all these apocalypse type scenarios, remember this EMP is, the wave that comes out of this is not some magic wave that just destroys everything right off the bat. It's RF energy of one type or another. It's an electromagnetic energy, which translates to RF energy. It's very, very broad band, but it's something we can deal with. The common way to deal with RF is what's called a Faraday cage. And usually it's a full metal enclosure or very fine wire mesh. I've worked in a couple in the past, and they're usually grounded. And the idea is it will not let any RF into that environment. Now, if you put something touching that metal screen, then yes, that device is going to receive some RF. But in general, if it's not touching that metal screen and it's inside of it, you're not going to see any RF. You can take a cell phone in there, it won't work. Two-way radios won't work. Even just across the room, they won't work. You know, if somebody's outside the screen and you're inside the screen, you can't talk to each other. So that's the idea behind Faraday cages. And the common perception is that a trash can is probably your best bet, off-the-shelf bet, to provide yourself with a Faraday cage. So I went down and purchased a trash can from the hardware store, just a generic metal trash can, made in America trash can, and just to see if it's true. I've never really tried it before. So we're going to try this, and we're going to focus between 10 and that 100 megahertz, where most of the energy is in that E1. And we're going to go below it some, and we're going to go above it some. I'm not going to go real high in frequency, mainly because I don't have anything here that'll go above 400 megahertz or 440 megahertz. So we're not going to bother going much higher than that. I may stick a cell phone in there and see what happens. And the spectrum analyzer we're going to use is a little RF Explorer. I tried to use my big 7550 IFR that I've had, man, I don't know how many years I've had that thing. Whenever I started my two-way radio business way back when, I bought that thing, and when I got out of the two-way business on the personal level, I kept that just because it's so handy to tune duplexers and whatnot. And every once in a while, I'll take it down and compare it to much newer equipment at work just to see if it's anywhere close to calibration. Surprisingly, over the last 10 years or so, it's stayed pretty close to where it was the last time it was calibrated. So I took this little RF Explorer and compared it to that 7550. I had to use the same antenna, because if you use different antennas, you'll get completely different results. But using the same antenna with an adapter to make it work on both machines, it was actually closer than I thought it would be. I wasn't expecting much out of this little outfit. I don't remember how much it was, but I wasn't expecting a whole lot out of it. And this is the version that goes clear down, I think, to 50 kilohertz. And surprisingly, most of the time it was within 2-3 dB of the 7550. Usually it was closer than that. A little bit of difference, but all in all, it's accurate enough for what we're testing. And we want to see how much RF, if any, gets into this trash can, and if it's good enough to work as a Faraday cage. And I will contend that in most cases, I don't think you would need to block all the RF, but if you can attenuate it enough that the level's low enough, it's not going to hurt the equipment inside, I think you're okay. And the reason I say that is pretty much any electronics equipment in today's world puts up with some amount of RF. So unless you're living in complete boondocks USA, like out in the middle of Alaska, and even then you're going to get some RF from satellites above you, most of your equipment these days is getting RF into it in one way or another, especially if you live in cities, driving around, in places, very high RF environments. And I've never seen any modern equipment fail, like when we take it to up to radio sites where there may be a TV transmitter putting out buku power. There's a lot of RF getting into that device, and it doesn't kill the device. So most devices are able to handle some RF. So what we're concerned about is, can we lower the RF level enough to make it safe? So let me show you the setup we're going to use, and then we'll start our testing. So here's the can, just an off-the-shelf can from the hardware store, nothing special. After the testing, I will go through and explain some things that we could probably do to change this and make it a little better, but I wanted to test it just like it is. So there's our little analyzer down there, and it's on blocks of wood. Nothing's touching the outside of the can, and I'm going to test this ungrounded this first time through. And originally my idea was, just leave the lid off, test it like that, and then put the lid on and see what the difference is. But on the lower frequencies, this can already blocks a great deal of the RF energy. So what I did is I marked a spot on the floor. We'll put that meter right on that spot, test it outside the can. The can will be moved away, and then I'll move the can back in place with that inside of it like that. We'll test it with the lid off and the lid on, and then we'll compare the three and see how much protection this can gives us in the different scenarios with the lid off and on. And this is going to be, I'll be right up front, completely unscientific, because my antennas are at different distances away from this can at the different frequencies. So the energy level that's getting here is going to be different to whatever degree depending on the frequency. Originally I had planned on using a service monitor with an external amplifier that boosted up to I think about plus 15 dBm, but today I found out my amplifier is no longer working for that old service monitor, so we're going to have to just do it this way with just RF from a radio. Again, it's not scientific, but it gives us a good baseline to figure out how much attenuation one of these cans offer us. So with that, we'll get started. We'll start at the low frequencies and work our way up to 450 or 440 some megahertz and see what results we get with this can. So this wound up being a pretty fun experiment for me to play with. And yes, I made sure to ID when I transmitted on those. You just didn't see it on video, but I made sure everything was the proper identification when I transmitted on ham bands. So don't get all freaked out. What can we draw for a conclusion from any of this? Well, it's not going to be a scientific conclusion, but there's some general conclusions that we can draw. Let's look at this chart real quick. And one thing I want to mention, if you're not familiar with the dB scale, which is used here, the dBm, you'll see on all these numbers, is you'll notice those are negative numbers. So minus 75 compared to minus 95, minus 75 is a much larger signal than minus 95 because they're negative numbers. Look up the dB scale. I don't want to dive into that right now, but you can read about it. Just remember, these numbers are negative numbers. So minus, for just instance, minus 75 and minus 100, minus 75 is a much larger number. So if we look at the 1.84 megahertz, which this, I was hesitant to even include this because my antenna was really acting up. So I was not able to get a very large signal coming to our meter here. And the other thing I'm going to mention is with this can, minus 115 is about as low as this meter will read accurately at all. And so I'm going to use that as the bottom scale. Even though we didn't get a reading at the bottom, I'm going to use minus 115 for the bottom so we can say it will attenuate at least to this level. And one of these days I may redo this experiment and get the can much closer to an antenna so we can get more accurate readings of how much this truly attenuates. But I didn't feel like diving into it on this video. So the 1.84, we can see that from inside to outside the can, we've already got 26 dBs of attenuation. And we put the lid on. Again, I really don't know where this is. It's probably going to attenuate much more than this, but using minus 115 at that bottom, we get 40 dBs of attenuation there. 3.56, we've got, now I'm just going to jump from outside to inside the can with the lid on. And then we'll look at the inside without the lid here in just a second. So 3.56 megahertz, we've got 56 dBs of attenuation. So 7.11 megahertz, we have 65.5 dBs of attenuation. 14.11 megahertz, which is, I want to point out, within the 10 to 100 megahertz range that we're really concerned about. 75 dBs of isolation. 28.11, 59.5 dBs. 50.11, which we're now in, all these other frequencies were HF or high frequency frequencies. 50.11 is actually a VHF frequency. It's low band VHF, but it's still VHF frequencies. 67 dBs of isolation, at least. Now I want to say at least on all these because, again, we don't know where that actual bottom end is. If we get a much stronger signal next to this can, we may be able to figure out the very, what this truly attenuates at. But, you know, we're giving at least this amount of attenuation, at least. So now let's look at 146.55 megahertz. And this is kind of mid-range VHF frequency. And VHF, very high frequency, by the way. So at that frequency, we actually saw a little signal creep into the can. So we can get a true measurement of how much this thing's attenuating at that frequency. 74 dBs of attenuation there. Now, once we jump to UHF frequencies, 446.55 megahertz, which is well outside the 10 to 100 megahertz range that most of that pulse contains its energy, but still there'll be energy at this frequency. Quickly, let's go back and look at outside the can versus inside the can with no lid on the can. We can see the HF frequencies, you got quite a bit of attenuation right off the bat, you know, kind of roughly the 30 dB range of attenuation just by placing it inside the can. And real quickly, this dB thing, if you're not familiar with the dB scale, for every 3 dB roughly, you've got half the signal strength. So or double the signal strength, whichever way you want to look at it. It can go either way. But let's look at loss here. So let's just take, this is kind of an odd example, but let's take 1 watt and you've got 3 dB of loss. Well, then you've got half a watt. Well, if you've got 6 dBs of loss and you're starting off at 1 watt, you've only got a 1/4 watt, because 3 dB, you've cut it in half, and then another 3 dB, you've cut it in half again. So you're down to a 1/4 watt. Does that make sense? Now, once we get up into the VHF frequencies, we notice that this changes. The higher the frequency, pretty much the less attenuation we have just by placing it in the can. And the reason for that is the wavelengths are getting shorter and shorter. Like down at 3.56 megahertz, that wavelength's roughly 80 meters long. And if we jump to 50 megahertz, now we're only down to 6 meters of wavelength. And the 146, well, that's only 2 meters. And 446.55, well, it's 70 centimeter roughly wavelength that we're talking about. So the higher the frequency, the shorter the wavelength. So it's able to get into smaller holes, and that's the reason on microwaves you'll see the little tiny screen that you can see through. They put that there so you can still see in, but it's blocking the RF from coming out. Any of that make any sense to you? So the general conclusion is this can works really well at attenuating HF frequencies, which is to be expected. The long wavelengths are not going to find the little nooks and crannies to get into that can. The VHF and UHF is getting into that can, and in fact the UHF, you're seeing far less attenuation at the UHF frequency than you did at the VHF frequency. So I kind of want to wrap this video up. I want to come back to this experiment and do a few more things. One, ground this can, get it closer to the antenna so we can find out what the true performance is at HF frequencies. And the other thing I want to mention about this can that I have is it's got little holes in it where the handles mount. I have an old can out in the shop, and if I can find the lid for that old can, the handles are welded on that one. And so it doesn't have little holes in it. I want to see what the difference is those little holes make. If I can find the lid to that big old can I have out there. And it'd be interesting just to see what the difference is. And then maybe test some other things that are commonly referred to as good Faraday cages, like gun safes, ammo cans, things like that. And maybe even make a little small mock metal building with some just regular tin on it and see how much it attenuates radio signals, maybe grounded and ungrounded. It'd be a good experiment to try. So again, I'm going to come back to a lot of this and try and get these experiments a little better, but I didn't want to dive into all that in one video. So we'll come back to a lot of this later and look at it again. And I'm curious to see how it all turns out. I'm really curious to see what the difference is between grounded and ungrounded on this trash can idea. So thanks for watching, subscribing, giving us the thumbs up. Now, I hate nagging everybody for the subscribing and the thumbs up stuff, but that's the way YouTube works. And we need those to promote the videos. If we don't get that, the videos don't seem to get promoted as well. So I'm going to keep nagging you for it anyway, even though I hate to do it. I sound like an old nag. I know. So until next time, have a great one, and we'll see you guys on the next video. And yes, sometimes I know I talk a little slower. If I don't, my mind gets ahead of what's coming out my mouth, and what comes out just doesn't make any sense.
What you talking about, Will?